Okay, in this lecture, we are going to be reviewing phase diagrams. Now, in class, we talked about the initial idea that phase diagrams show that the melting point or freezing point on this boundary line is not static. Okay, it can change with changes of pressure. And of course, we've already talked about from table H a few months back that the boundary line or the a boiling or condensation point is also can be changed. And of course, we did not talk much about is that boundary between solid and gas, okay, sublimation if we're going from solid to gas or deposition from gas to solid also is not fixed. And of course, we mentioned the triple point, which is the place that tells that all three phases of matter can exist together at equilibrium. We'll talk more about equilibrium, but they're all there at that temperature, and every compound has a new. Now, we did not talk about, of course, every compound has a unique point there. What we did not talk about is this critical point. But before I get there, I just want to compare um, the phase diagram of CO2 with water. There's a couple of pieces there to look at, or differences. Okay, so let's move on to the next slide, so to speak, if I can. So here's the phase diagram of water. And you notice its triple point, of course, as we talked about, is lower than 1 atmosphere. So at 1 atmosphere, as temperature increases at constant pressure, you can see that the solid becomes liquid to gas, as we notice. Now, if we were at a lower pressure, okay, lower than 0.006 atmospheres, almost a pure vacuum, we would have a sublimation. So very little sublimation occurs with water. Okay, however, you've heard of freeze drying. Now, freeze drying, of course, is we take something like strawberries, why not, and we freeze them. They have water in them. So we take strawberries with water, we freeze them at constant pressure so they go this way. Now they're a solid. Now what we do is we put them in a vacuum, and when they're frozen, we put them in a vacuum and we drop the pressure, and eventually we can see that the solid water that's most fruits are made up of become a gas. And freeze drying is just that. Take the liquid of the fruit, freeze it, and then we put it in a vacuum, and then we sublime or sublimate all of the water out, and it becomes dried. And the gas, of course, just leaves the reaction container. Freeze dried coffee beans, same idea. Okay, but we have to drop the pressure pretty low to do that. All right, but something else to think about. Look at CO2. Look at CO2 again. Look at this slope of this line. Okay, positive. Okay, notice the more dense phase is the solid. Now look at water. The next slide I'm going to move to. Look how it's the negative curve or a negative slope. Okay, what again? Let's look at the slope right, the boundary line between solid and liquid. Look at that for a second. Yeah, it's totally different. And CO2, as the temperature drops and the pressure increases, the most dense phase is solid. But water, because of its unique crystalline structure that has spaces in it, because of H bonding crystalline structure, okay, we noticed actually as if we were to extend this line, at some point, liquid is favored. Now, there's something unique about water. If you're on solid ice, like right here, okay, let me see if I can, if I'm solid ice right here, and if I was to increase the pressure, it would become a liquid because this line bends this way. Think about someone standing on some ice skates. So if I'm a 200-pound person, and I'm thinking positively, and I'm on very, very thin ice skates, all my mass or the weight is on a small, thin piece, a blade of steel. It's a lot of pressure. The pressure is high. So by sitting on a little thin amount of steel with all my weight on a little piece, the pressure increases. So as you put all your weight on a small piece of metal, the pressure increases and you become a liquid. And that liquid allows the static of coefficient to be significant enough to glide over the solid. So we create liquid as you skate. All right. Now, some people also suggest the skating, the friction between the metal and the blade also creates heat, which also melts. And that's true, but also the pressure is increased and we can create some liquid to skate on. Now CO2 does not allow that to happen. Let's go back to CO2. If you have a liquid and you try to skate on the liquid, maybe you create a solid if that's true. But if you're on solid CO2 or solid asphalt, because most compounds have this slope here between the boundary of solid to liquid. Remember, water's a weirdo because of its crystalline structure. Its most preferred phase is actually liquid over time, but CO2, CO2, if you're at a solid phase, increase the pressure, okay, it's going to stay solid. Just like you can't skate on rocks, you can't skate on sand, you can't ice skate, of course, on CO2. All right, and that's something to think about. And also, when you compare these guys, okay, you can see the differences there. The chill point is much, okay, higher for CO2. That's why in class today you saw that we existed in this area. And notice the sublimation temperature is negative 78 degrees Celsius. So if you had that dry ice in your hand too long, the temperature at which the dry ice goes from solid to gas is negative 78 or negative 80, as I was saying in class. Cold stuff. But water, because our 1 atmosphere is here, we're above that triple point. Okay, now there's one more point I haven't talked about, and it's called a critical point, and it's right here. We've talked about the triple point, the critical point. It's a pretty unique scenario here. In the triple point, that's a scenario where the temperature is so great that a liquid wants to become a gas, okay? But the pressure is also so great that liquid can't completely be a gas because the pressure pushing on it, okay, makes its density less than that of a gas, about half as much, depending. This gas with high pressure wants to be a liquid, but with the high temperature, it overcomes its attractive forces. Remember, gas on high pressure is being pushed together. Most gases become liquid. As you start here and you increase the pressure, you become a liquid. Push gases together, they become liquid. So at this point, it can't do that because at this unique temperature and pressure, this gas with that amount of temperature has too much energy. And therefore, even with increases in pressure, it can't quite be a liquid because it's got too much energy. So it's something in between. The gas has too much kinetic energy, so it overcomes the attractive forces even at high pressures. And a liquid, okay, although has enough kinetic energy to be a gas, the pressure keeps it from being a complete individual particle. So what you have beyond this critical temperature and critical pressure is you have something called a supercritical fluid. Okay, SCF. And these supercritical fluids are very important chemistry that's going on right now. They're very important because they're able to dissolve exactly one component. Case in point, back when I was your age, caffeinated coffee was the new thing. But the decaffeinated coffee, I should say, was not pure caffeine free. It was about 10% free. So what they did is they lowered the amount of caffeine, so people that weren't, addicted to caffeine and having high stimulus type days, okay, racing their nervous system, they tried to limit the amount of caffeine. So what they did was, when they dissolved the caffeine, they couldn't help but take out flavors because the caffeine, being mostly nonpolar, would also have other nonpolar components like the flavors of the coffee, okay, that were very similar in solubility. So when they dissolved the caffeine, they also dissolved a lot of other chemicals that were similar in solubility, like the flavors. And people hated the taste. It was barely decaffeinated. People, what's the point? Now decaffeinated coffee is about 95% decaffeinated and tastes the same as caffeinated coffee. Well, how? They're able to dissolve just the chemical, like the caffeine they want. And they do that with supercritical fluids. And how do they do that? When you change the pressure and temperature of a solvent like CO2, even though I have water here, CO2 is a very common solvent, you can actually dial in with the pressure and temperature above this point to match the exact solubility of a compound. And what happens is we'll take a supercritical fluid like CO2, and we can actually increase the temperature and pressure beyond this point, somewhere here or here or here, and that supercritical fluid is able to dissolve just the caffeine if we just dial in the exact degrees Celsius and pressure. And that's able to um, just dissolve just the one chemical, like the caffeine, and leave the rest. And all you got to do is decrease the pressure, okay, or decrease the temperature. So you decrease the temperature and decrease the pressure, and it becomes a gas. Most of the time, we just decrease the pressure, and it becomes a gas or and temperature. Some point. So if you're at this point, okay, decreasing the pressure, it becomes a gas, and the CO2 leaves. All right, so supercritical fluids. Now, they're trying. Fat-free foods are often done this way too. Years ago, fat-free foods tasted horrible for the same reason. With supercritical fluids, now they can dissolve just those components, and it has bigger implications. Um, they're thinking and they're developing a supercritical fluid just to dissolve, okay, metastasized cells, cells that are cancer cells, and able to do just dissolve them in the body, okay, and not harm the surrounding components. Usually, surgery, when you take out cancerous cells, it's pretty invasive, and you can potentially hurt other organs it's attached to. But if you can just go in and somehow have a solvent that can actually just dissolve just where the cancer cells are, just a very specific solubility, think of those are tremendous implications. Also, organic solvents that we use in preparation of pharmaceuticals often have adverse side effects because of the solvents used to make them. Now we don't have that issue as much. A lot of implications here. And there's a movie I'd like you to watch. My favorite, one of my favorite chemists out there, University of Nottingham, it's his research area. So please look at that. So that's basically what I wanted to cover. I think I have one more slide here before I want to stop. Okay, and that's iodine is interesting in that its critical triple point, sorry, is well below 1 atmosphere. So it's supposed to have all three phases, but we notice that iodine sublimes, and it's a weird scenario. The intermolecular forces between the iodine molecules are not strong enough to keep them together in liquid state. So what they happen to do is iodine will actually become a liquid, okay, but because they don't have enough energy to stay as a liquid, they quickly become a gas. So it's interesting that the basic phase diagram is this for iodine, but yet we see it become a gas. So again, the intermolecular forces between the iodine are not strong enough to keep together in the liquid state after they gain enough kinetic energy to break free. So interesting enough, we see it sublime, but the phase diagram suggests that it really doesn't. It just evaporates very easily. And look at this. This is a small scale. All right. Any case, should be a small scale, 113 to 118, 184.5. So the boiling point shows it's pretty high, but its vapor pressure is pretty high. So it's kind of a weird scenario altogether, but I just figured I'd throw that in. So we're going to pick up right here, and you should be able to figure out all these points in the phase diagram as I talked about before. Remember, you have the notes. Okay, so take care.